So the last presentation is entitled Three-Dimensional Photonic Manufacturing of Architecture Metamaterials from Professor Nicholas Fang from MIT. So Professor Fang.
Good evening, good afternoon, or good morning, depending on where you are. Thank you very much for attending this exciting workshop. I really wanted to take the opportunity to thank the organizer for the opportunity to share our research on the effects related to manufacturing of architecture metamaterials. My name is Nick Fang. I'm a professor of mechanical engineering from MIT. And I'd like to give you just a quick overview about our research. As many of our guest speakers, we started as a photonic group looking at how light or other form of electromagnetic wave become concentrated and converted into smaller and subequivalent scales. And we learned from those fundamental processes of light conversion, light harvesting, and light emission at small scales to apply it to different applications of light and sound. And through the process, we also explored and developed the technologies, including those micro and nanofabrication tools that will bring different materials, metal, ceramic, polymers all together to enable the different optical, acoustic, thermal applications that are embedded in those functional structures. So the talk that I'm giving today will be focused on our ongoing effort that are not only providing those acoustic, light, or electromagnetic functions, but also considering the importance of load bearing or survival in extreme environments such as thermal shocks, fatigue flow, and so on and so forth. So if we are able really to combine the physics of both, I would say the wave engineering or wave physics domain together with the requirements of load bearing and other thermal management requirements, then it is possible to broaden the scope of metamaterials for important areas such as RF domains. We hear in the previous talks on applying, for example, conformal antennas. We are also very much interested in medical implant as well as high throughput gas or liquid filtration. So how to bring this together into now a structural elements inspired by, for example, the so to speak the 2D spectrum space that is enabled by, for example, blending 4 different colors, CMYK, in the inkjet printing space. Now we are actively searching the 3-dimensional equivalent with now the physical properties that can be, correlated to a library of such digital voxels, 3-dimensional lattice structures that not only is, highly porous so that you can tailor its permeability based on the density, but it is also possible to change their, thermal expansion so that, for example, over a wide temperature range, you may be able to maintain the structural integrity and even a small temperature effects with respect to RF, EM, light, or other properties that the substrate will be able to maintain. So if you are interested in some of the details, the following paper in the physical review letters highlight some of our earlier attempts of that. And I would say that lightweighting is a very promising direction. And taking, so for example, fiber composite as an example, or some of the foams that you might have been using for example, for the antenna applications, it is really important to recognize that the connectivity of those lightweight elements are actually essential for their mechanical, acoustic, thermal properties, and so on and so forth. Our earlier effort was really made possible by two rising stars in the field, Professor Ren Zhen, who is now at the UCLA, and Professor Hong Li, who just moved from Rutgers to Seoul National University. So they examined particularly these unique structures of so-called octet truss elements. So if you build a octet truss lattice made out of those now tiny micro beams and structures, then a surprising fact is emerging. You could keep their density as low as that of aerogels. In other words, their permeability will be permittivity will be comparable to air. On the other hand, when you try to bend or compress those materials, you see that they actually can be as stiff or as say tough as engineering rubbers. So for the same density of the aerogel materials, we are actually enabling now more load-bearing capabilities on such unique lattice-based metamaterials. And not only you can kind of tailor their load-bearing capabilities upon compression, you could also potentially say change the effect of such lattice structures by upon stretching. Here, in the earlier work published in Nature Materials in 2016, we showed that by combining both bending and stretching effects in such lattice structures, you could overcome some brittleness of the bulk materials. Here, this nickel phosphate microlattice can be even stretched by up to 12%. So it is no longer really, just as brittle as the bulk counterpart. And more recently, we have been looking at the opportunities to generalize the design of such complex geometries, so that we could now say really bring different characteristics, the physical properties, such as the electromagnetic permeabilities and permittivities, together with important, say, thermal response or mechanical, say, load-bearing effect. Here, there's a really like a rich space of literature that pioneered on these studies. Some of the work, for example, from Martin Wagner's group at the Karlsruhe Institute of Technology, highlighted the possibilities to tailor such a lattice so that it will actually exhibit a negative Poisson ratio. So what are the general guidelines? It turns out those complex geometries sometimes are difficult to say predict because there are different deformation modes that are embedded in those lattice structures. But scaling analysis actually help us to outline some important trends and offer insight of how such structures can be inversely designed. Generally speaking, we are actually looking at the two important topologies, truss-based elements or beam elements, as well as the thin shells. For example, for the case of closed forms, we are really looking at how the shell layer bends and stretch under different loading. So one of our PhD candidate, Huifeng Du, is taking a brief step to generalize such a concept in collaboration with a research group, Professor Rashid Abdul Rab group at the Khalifa University in Abu Dhabi. They looked together this unique lattice structure, so-called Tripoli minimal surfaces. This is actually a structural element found widely in bicontinuous phases. Many biological materials incorporate such geometry. And it turns out that if we are trying to examine the mechanical behavior of such elements, you can also say group them into the different deformation modes that are basically distributing the load by the skeletal bending, stretching, as well as sheet bending modes. And each of them has a different scaling laws in terms of reducing, for example, the weight or volume ratio of individual elements. And interestingly, this scaling effect can be also deduced, for example, not only in the elastic domain, but also in the case where the structure is under large deformation, for example, densification as well as plastic failure. So we found a very say nice library now in the scale of micrometers and millimeter. And our next effort is to really trying to expand that into the smaller dimensions. And thanks to collaborators such as Professor Xuanhe's group, who are looking to the say interfacial challenges here. We see that it is promising to now say design those child or topologically optimized say triple minimal surfaces so that we can completely capture their mechanical behavior, not only in the densification but also up to the the plastic failure regimes, so that we can now provide important feedback to tailor the geometrical the topology as well as the surface bounding requirements. And in the long run, we expect those structures will be not only say lightweight but also tough, so that they can survive under severe environments, including impact resistance as well as cyclic thermal shock. And a very important attribute of such a lightweight substrate and materials actually are found in the transportation space. In the previous talk, we hear that we can actually use some of fiberglass absorbers, for example, in support of the conformal antenna design. But in the acoustic domain, there will be also very similar needs. And in this case, we are looking at now shell or say enclosures that are thinner and lighter weight, for example, to bring fuel efficiency higher. Unfortunately, in this case, we are seeing a similar a limit of say the material thickness versus the acoustic absorption or soundproof efficiency. And earlier studies by Ford engineers pick up this as actually one of the most serious challenge if you wanted to now reduce the fuel consumption while maintaining acoustic comfort on a road ride. Then we have to look into solutions beyond the current synthetic fabric or so to speak, matte type of solutions. So in collaboration with Professor Minghui Liu's group at Nanjing University, we identified a unique case of the metallic foams. In this particular example, the foam itself is already providing substantial strength so that it can work quite well for the load bearing. But unfortunately, you can see that the acoustic absorption is not something that the metallic foam actually is capable of. On the contrast, when you examine acoustic absorbers from the natural fabric and natural materials, you see that many of those fibers and fabric materials are actually carrying a feature size or dimension that is quite different from what you observe in the say foam lattices. So here, combining now the required, so to speak, features that are compatible to acoustic boundary layers, we show that those engineered metallic foams can really take the merit of both excellent sound dampening, close to 90% of acoustic absorption, while maintaining the stiffness of the metallic forms. So many of the secrets of the micro and nanoscale effect can be now incorporated in such a unique lattice element. So this is actually, again, just the very beginning of the story. We are looking into many important challenges in terms of sound dampening and error permeability and so on. And I'm sorry, this is really like we had great opportunities actually to participate ERC collaboration as a international member, and through that we were able to host two research collaboration. Professor Jesus Carvalho San Martin, actually from University of Alicante, come and collaborate with us on the now again thin and error permeable microporrated acoustic absorbers, and we see that it is indeed possible to reduce the overall thickness by leveraging some unique channel designs, as well as increasing the acoustic boundary layer thickness in those fine features. And together with Professor Zelinsky group at the ITFR in Poland, we also formed a round-robin studies looking at the different acoustic absorbers formed by same geometry, but using different additive manufacturing processes. We see there is actually important features related to the surface finish, surface channel tutorosity, and so on, that are all coming from different materials and fabrication processes related to the additive manufacturing. So noise, fighting noise is again a very important international challenge if we wanted to really provide a quiet space for the now increasing population in the metropolitan area. With that, let me switch gear and talk about the manufacturing challenges that we are encountering in this particular domain. So we hear in the earlier talks that there are different needs, for example, for photonics and RF functionalities. Very often those are made possible by, for example, embedding metallic components or conductive species. And in case of increasing magnetic permeability, then very often you will need embedding, for example, oxide materials, or even garnet type of special substrate. And we are looking at the very different features. Some of those are responsible for heat conduction. Some of them are responsible, for example, for tuning the thermal capacity and conductivity. So we are really going beyond what is typically offered as a so-called printed circuit board technology or thin film deposition. Instead, the material set that we need should be really compatible with a wider range, and it should be also amenable to heterogeneous structures. So to meet that kind of stringent requirement, we have been evaluating and comparing different available microfabrication and additive manufacturing tools available currently. So some of you may have been already using, so to speak, the direct extrusion or inkjet-based technologies for printing antennas. Well, those technologies are actually quite friendly in terms of the fabrication of large substrate. They often suffer or become constrained in terms of feature resolution. So for the case of acoustic absorbers that we are looking for, the feature size will be smaller than 50 micrometer, and sometimes this is not feasible for the extrusion-based tools. On the other extreme, we see that many exciting research are being emerged using this so-called two-photon lithography method pioneered by Professor Martin Wagner's group at Karlsruhe. However, associated with this fine lines that are subwavelengths in the optical domain, you also see a requirements of finite sample size, sometimes in the order of say millimeters and less. This is because generating each of the pixels will need now substantial movement and coordination of the material solidification, and that on the other hand make these tools yet to be developed for a larger scale and I'll say suited for say cost-effective evaluation. So in that domain, we have been pursuing the so-called projection microseries lithography tools that bridge the gap between extrusion and I'll call two-photon lithography-based rapid prototyping and manufacturing processes. And currently, we are able to already generate something that is of the scale of 25 centimeters and so, and yet maintaining a feature size of micrometers or smaller. So how did we do that? We find that there are a couple of challenging issues that limit the scalability of this photonic-based process. One of them is associated with the, so to speak, adhesion and friction that are required to move the fluid. The thinner the fluid, the say higher the so to speak viscosity or pressure drop that we have to combat with. So here, in collaboration with Professor Yanling Song's group at the Institute of Chemistry, we are able to say minimize the surface adhesion between the say spreading of different liquid layers. And by doing so, we can now really generate a ping pong ball size of, for example, these Buckley structures in the order of a few minutes. And similarly, we can now also minimize the use of some of the expensive, I'll say, functional materials, say, for ceramic resins. Some of those compounds are actually of hundreds of dollars per gram. So we have to really now minimize their waste. Here we see that such improved surface lubrication also give us the new avenue to achieve that goal. And I mentioned the scaling issues. So today, if we are looking at the current, so to speak, layer by layer technology to generate the metamaterials, then very often we are actually constrained by the format of the display or images that are provided by the display devices. Today, even for the so-called 4K displays, we are really in the order of hundreds of megapixels. And when you shrink those individual pixels and form the metastructures, then we are actually seeing the constraints of the surface area. So sometimes in optics, we consider this as the intrinsic limit of the spatial bandwidth problem. So if you wanted to pursue a fine feature, then you have to also sacrifice the area at which the pattern is being projected. So Professor Siu Kim, who just joined Changwon National University, conceived this idea of using, say, new projection tools so that we can now successfully push the projected pixels from in megapixels all the way to terapixels, 6 order of magnitude improvement in this case, while maintaining the feature size at a few micrometers experimentally. So how he did that? He leveraged the use of now the lenselet technologies of micro lens arrays. Today, it is possible to obtain even say large sheet of micro lenses containing, for example, individual elements or imaging units of say 100 micrometers and smaller. And by coupling that with for example, digital displays, which already contains megapixels of megapixels of display, it is possible to take a modulation so that the projected image is actually the convolution of the two imaging elements. And by doing so, we see that on the bottom, not only it allows say large format while maintaining fine features, it also enables and incorporate some aperiodical designs such as rotation as well as say twisting in this large meta surface or meta structures that can be readily prototyped now in the say thickness of centimeters and above. So with that, we having also actively collaborating with different field experts. Here, I'm showing you that by printing and incorporating different mechanical elements, each of them actually can be tailored with different stiffness and compliance. We are now able to even generate a completely new engineering scaffold that can support the growth and proliferation of important vital tissues. Here, as an example, neurons actually would like to say propagate and connect on a relatively stiff, relatively soft, say fiber element. Our glial cells surprisingly has a stiffness that is lower than gel. So here we show that by tailoring the say photonic exposure of individual fibers, we are able to form say pillars that are smaller than the 10 micrometers in diameter and heights of 100 micrometers and even beyond. And by doing so, we can form both horizontal and vertical pillar arrays that serve as a conduit for the both axon and glial cells to migrate and even wrap around those pillars. And for the first time, we see that such a myelination recapitulates some of the important development biological processes that are important for example, for the brain formation. And we look forward to the more, I would say, important field studies using those tools to identify and isolate biological as well as mechanical cues to support neuron formation in now a chip level. And this architectured materials is not only important for again implant or scaffolding for tissues. We are also actively looking at their say potential use now in the, for example, bio or microstructure reactions. So on the top, what I'm showing is the high density microelectrodes that shows promise to increase the power energy density and power density beyond, for example, what is currently generated using, for example, the layer by layer approach, for example, for lithium ion batteries. our preliminary results already show that again, a factor of 6 improvement can be achievable simply by changing the electrode orientation into the 3D lattice domain. And we also have been actively looking at the opportunities, for example, to leverage the thermal stress using the now light density and confined architectural structures that I mentioned before, while maintaining the high surface to volume ratio. By doing so, we expect that the ceramic catalytic converter can now reduce the pressure drop, in other words, enable high throughput waste gas processing. And this has been a very important challenge both in the US and probably also in the Middle East and European Union. So today we are facing a stringent requirement from regulation to reduce, for example, the volatile gas emission by 70% in year 2025 or beyond. And this is actually a important health threat to people living in the larger area, a larger population area. And why this is a so difficult problem? It turns out that there are already commercially available the catalytic converters in the market. But when you turn on the car, the first few cycles of the engine start actually is really the problem of the so-called cold start gas release. And at that time, the catalytic converter is not yet at the right temperature, and it cannot really efficiently convert now the waste gas such as carbon dioxide or nitride oxide. So, how do we address this particular issue? It turns out that within that beginning 10 cycles, we really need a substrate that can heat up in a few seconds. And here we show that such architected ceramic materials made by, for example, the hollow tube ceramic, when it is subject to, for example, a immediate heating using, say, a high temperature flame, you see that the inverse process here. Once the flame is turned off, after 2 seconds, the lattice already start to cool, and at the 4-second range, it really goes back to the ambient temperature. On the other hand, if you are looking at the case of the monolith honeycomb structures, you see that the increased thermal mass in these honeycomb actually is responsible for longer time response. And as I mentioned, this is really the limiting factor for such a converter to address the cold start problem. So we do see that architectured ceramic now providing a promising solution to increase the filtration efficiency and reduce the, for example, pressure loss in this challenging environment. So when we are looking at the architected metamaterials and structures, we see that not only it reduces the use of critical materials for lightweighting, but it also provides opportunities to increase heat transfer, reducing pressure drop, increasing our tailored mechanical strength and compliance. And in the future, we think this may find application, important application areas in terms of filtration for gas and water, and also maintaining the important thermal management, for example, in the confined space. This could be also very important for antennas and other, say, light emitting devices. And yet, there are many open questions that are in the manufacturing and design space that we look forward to collaborations across different disciplines. And with that, I'd like to thank my students, academic collaborators, and not last but not least, international industrial collaborators as well as funding agencies. And thank you very much for your attention.
Thank you very much, Professor Fang. Very interesting talk, very interesting demonstration of capabilities. So we have a couple of questions. I think we can go quickly through it. So in slide number 6, you mentioned that you have the same Collin effect for plastic failure. Which constitutive model you have used for this?
Right. So this actually constitutive model depends on what particular material we are building the lattice with. For metals, we are actually looking at elastic plastic behaviors of for example, thin film metal material. And for the plastic materials, we have been using Neo-Hokian, but I think it is very feasible to apply other models such as the famous Aruda and Boyce models, for example. Yeah.
So, and we have a last question here is there a way to take advantage of the atomic lattice structure for the 3D voxels?
Absolutely. I think this is the eventual goal is really to kind of connect I'll say the structural elements all the way from atomic structure to the millimeter and the centimeter scale. I would not give you an example of atomic lattice, but we can say that, for example, for polymers, changing the crystallinity of the polymer fiber, you could expect that a strengthening effect. And a study conducted by my colleagues, Professor Gang Chen, to show that the thermal effects, thermal conductivity of those elements also increased dramatically with a result comparable to stainless steel. So I think there is many open avenues in the very bottom.
Okay, so and yeah, Dr. Ziner, please.
Yeah, I have just not really scientific question, but you talk on manufacturing need for metamaterial, that it isn't really expensive, that it could be scalable. Did you have like a range of cost of this 3D printed material?
Yeah, so the cost of those 3D printed materials will vary based on, I would say, the volume as well as the precision you manufacture those. Today, I think for a prototype or say a scale of like 10 centimeters and so, we are already arriving at something of say $10 per piece. So I don't think this is prohibitive compared to those that are made by other precision engineering tools. There are still a lot of say questions related to, for example, the use of specialty materials. For example, we don't have a direct equivalent of LTCC ceramic that can be immediately used for antenna application.
Okay, thank you.
Okay. Thank you. And finally, there is a question here regarding the thermal properties. You showed your structure cools down slower. I might not get it, but does it also heat up slower?
Oh, actually, I'm sorry if I confused you, but we actually have two structures in comparison. The structure that cools slower is the current catalytic converters using honeycomb ceramics. But the structure that we design actually cools down faster. So, it cools faster. Implies that if you heat it up, you actually also can heat up very quickly. In 2 seconds, it will heat up.
Understand. Well, thank you very much, Professor Fang.